quantum is the minimum amount of any physical entity. Matter is made of quanta, but also light is composed of quanta, which is called photons. So, in essence, this is a quantum.
Welcome everybody to a new episode of Your Friendly Physicist and Other Nerds, your science podcast where scientists speak about their fantastic research, their visions, dreams, challenges, and their daily life in the fabulous world of science. My name is Lucas, I'm your friendly physicist, and recently I got many questions from this podcast community about quantum mechanics. So I thought, why not doing a special episode where the basics of quantum mechanics will be explained? And I have just the perfect guest for this. His name is Gian Inkof. He studied physics and did a PhD afterwards in theoretical condensed matter physics, where he specialized on holography. Holography is a mixture of quantum mechanics and general relativity. So you see, he is just perfect to explain all your questions about quantum mechanics. I'm very happy to have you on board, Gian. Welcome to the show. How are you doing?
I'm good. Thank you for having me.
Great. So before we jump into the basics of quantum mechanics, a first question that is a ritual on this show, since the title is Your Friendly Physicist and Other Nerds, I have to ask this, Gian, are you a nerd? What would you say?
Well, partly yes, partly not. So in the middle, I would define place me in the middle.
That's a very good answer. Always being in the gray space, not being black or not being white. That's good.
Yeah, as always.
That's actually a good start for talking about quantum mechanics. But since I think, quantum mechanics is also never really black and never really white. It's always something in between. But we'll come to that later. Yeah, the topic is quantum mechanics. Let's start with the most basic question. What actually is quantum mechanics?
Yeah, the basic question, which is the hardest one.
They always are.
Yeah, but in a few words, quantum mechanics explains how small things work. And we have the laws of classical physics, right? But those laws cannot explain everything. For example, they cannot explain the results of some experiments on very small systems, and therefore they need to be corrected. And quantum mechanics is, if you want, a more sophisticated version of the classical Newtonian mechanics that is able to explain phenomena happening at the lowest length scales. Yeah, I would say in a nutshell, this is what quantum mechanics does.
So with small length scales, can you give an example? What are small length scales?
Yes, by small length scale, I mean very, very small objects like atoms that we'll probably cover this in the podcast, but atoms are some constituents of everything. Every object is composed of small, tiny little balls. And so we are talking about very small length scales.
So atomic length scales, which is nanometers.
Yeah, even smaller. Yeah, I'll run on nanometers.
Nanometers.
Yeah, they introduce an ad hoc unit of measurement for, when you discuss microscopic world. Yeah, the Armstrong is the correct length scale we should talk about. Yeah.
Okay. So quantum mechanics is kind of the theory of the small things in contrast to the large things. I mean, I think you mentioned classical Newtonian physics, which is about planets and orbits and cosmologic length scales. So really, large objects.
Yeah, exactly. I mean, when you're talking about such a large distances, even there, Newtonian mechanics doesn't work because we have to introduce general relativity. But basically, things that you see in everyday life can be, in a very good approximation, explained by the laws of classical mechanics. But everything you cannot see, so basically inside the materials and inside objects, cannot be explained so efficiently by classical mechanics. And you have to invent a new theory from scratch, which is quantum mechanics.
Okay. That's quite a cool answer. Okay, so it's about the small things. Then, second question, what exactly is a quantum? What is the quantum in quantum mechanics?
Yeah, this is another very good question. As we said, quantum physics is the science of the microscopic world. Okay, let's make an example. Think about the ocean. At first glance, the ocean appears to be a seamless mass of water, waves, and motion. Okay, imagine now you take a sample of water and you analyze it with a microscope. As you turn the crank of the microscope, you'll realize that water is actually composed of smaller and simpler objects. So zoom a little bit more, you will finally discover that the makeup of water is made of atoms, as we said before. So in the end, water is a collection of little balls, like marbles, which we call atoms. We could even zoom more and realize that as the water, the atom is composed itself of even smaller balls called particles. But I would stop here for a second and recap. The message here is that a complicated object like the ocean is a collection of a huge number of super small parts, the atoms. In a sense, it's like with buildings. Buildings are made up of small identical bricks, and in this sense, the bricks are the atoms of the buildings. And physicists introduce the word quantum to denote the bricks of the microscopic world. If you want more technically, quantum is the minimum amount of any physical entity. Matter is made of quanta, but also light is composed of quanta, which is called photons. So in essence, this is a quantum.
So the smallest possible entity of basically everything.
Yeah, exactly. But it's a very broad concept because it works with this image of the wall made of bricks, but also physical quantity are quantized. And there is the quantum of energy, and there is the quantum of light, there is the quantum of matter, and so on and so forth.
So when all these quantum physicists talk about, for example, quantization, they actually mean to break things down into what you said are the atomic bricks or the atomic marbles, like atoms.
Yeah, exactly. In a sense, is admitting and realizing that the microscopic world is not continuous as it appears to us, like the ocean, as we said before, but it is quantized. It is a collection of smaller objects.
Okay, I see. Great. I really like the picture of the ocean and the little marbles. Okay, so then another question that came into my mind, since whenever we talk about quantum mechanics or quantum physics, at some point Schrödinger's cat will appear.
Oh yeah.
What exactly is Schrödinger's cat, or what is the theory or the idea behind Schrödinger's cat?
Sure. Schrödinger's cat is a, let me say, highly unethical thought experiment, okay, that demonstrates the concept of a superposition in quantum mechanics, which is fundamental. So let's talk about this experiment. We have a cat, and that cat is in a box that, for whatever reason, contains a device able to release poison with a 50% of chance. Once we open the box, we'll discover whether the poor animal is dead or alive. However, until we don't open the box, we don't know whether the cat is dead or alive. It could equally be in one of these two states, or in other words, in a superposition of the states dead and alive. And this is how the quantum world works. A quantum system, like an atom, lives in a superposition of the possible states. For in the example before, the cat is dead and alive until we don't measure the system. When we measure the system, we open the box and we will see that the cat is either dead or alive. But before the measure, before the observation, the quantum system is in a superposition of all the possible states.
So all the possible states, meaning there are not just two, meaning dead or alive. This is just an example. There are multiple states your quanta can be simultaneously.
Yeah, exactly. This is just an example to start easy with the cat is a sort of quantum system with just two states. And the simplest superposition that you can have is a superposition of two states, but quantum systems can be more complex than that and can have also infinite number of states. And but the point is that when you measure uh, the system will present itself with a certain probability in one of these states.
So then it becomes a specific state. It's not superimposed anymore.
Yeah, exactly.
Okay. And the measurement, I mean, as I always understood it, measurement is kind of an interaction with this
Precisely. Yeah.
quantum object, be it a particle or whatever. So you measure it, you interact with this quantum object, and then it reveals its actual state.
Exactly. I mean, the observation, the measurement, um, is an interaction with the system itself. So you do this interaction if you want, you can explain the fact that the system prefers one of these states.
Okay, cool. Then we cleared the highly unethical experiment Schrödinger's cat, or Gedankenexperiment Schrödinger's cat. It is indeed highly unethical to killing a cat with a 50% probability.
Yeah, but no cat is mistreated in quantum mechanics. We're talking just about particles. So this is just, let me underline it, a thought experiment. So
Yeah. Another term that appeared quite often, or I read quite often, besides superposition, so a quantum object can have several states simultaneously, was the term entanglement. Can you explain what this is?
yeah, this is another property of quantum systems. And basically, we talked about states before, right? But the quantum states of two or more particles are not independent. They are correlated, even at large distances. So imagine, for example, you have two particles, particle 1 and particle 2, in two different bags. These particles can be in one of two states, say either blue or yellow, so no more dead or alive, blue or yellow, easier. When two particles are entangled, the state of one particle determines the state of the other particle, regardless of their separation. So, for example, imagine you leave your hometown, say Berlin, for a trip to Japan, and you bring with you just one of the two bags and leave the other at home. Once you land in Tokyo, you open the bag and discover the color of particle 1, say yellow. Now, quantum entanglement allows you not to call home to know the color of particle 2. When you measure particle 1, you instantly know the state of particle 2, even if it's located far away from particle 1. And this happens because the two particles are connected in a way that is not explainable by classical physics. And this is a unique property of quantum mechanics.
No matter the distance between those particles, they are somehow
Yeah,
connected.
yeah.
And let's say I change, for example, the color of the one particle from yellow to blue, then the other particle would also change its color.
Yeah, I mean, the two states are not independent. And they are, as you said, if you measure the state of one particle, since the other particle is correlated, is entangled with the particle you're measuring, you automatically know the state of the first one.
Okay. Is this, I mean, you said it's not explainable by classical physics, but is it by now explainable by quantum mechanics? So do we know why this is the case?
Well, from a theoretical point of view, I mean, when I first studied quantum entanglement, I didn't really understand why this happened. But because there is a even more sophisticated theory than quantum mechanics, which is called quantum field theory, which is basically, yeah, a more sophisticated theory, but that explain, for example, examples of particles are electrons, right? And instead of talking about different electrons, we talk about a field, which is like a fluid that is everywhere, and the particles are just the manifestation of this fluid into different points, but they belong to the same entity, the field. So entanglement in quantum field theory is more kind of built-in property in the theory. Yeah.
So this quantum field, is this then containing not just two particles, for example, two electrons? Then I imagine several
Any
electrons,
electrons.
any electron. So,
We're talking about the electron field, so just one guy, and that manifests itself through particles. Yeah.
so basically, every electron in this example, it's electrons. Every electron is entangled with all other electrons.
In a sense, yes. In a sense, yes. This is yeah, exactly.
Okay, so these are the two quantum mechanical properties, entanglement and superposition. So they can have different states simultaneously, and they are connected, meaning entangled with each other.
Yeah, superposition, if you want, is just specific on one particle that can be in a superposition of its own state. And then if you consider two different particles, there can be entanglement between two different particles. Yeah.
Okay, I see. Cool. So that basically also explains the so-called wave-particle duality. This might be then a superposition of a particle which can also be a wave, right?
Yeah. These are tightly connected concepts. Yeah. Superposition and wave-particle duality. Yeah. But maybe I could firstly explain what a particle and wave is. So, classical particles, I mean, we can think of classical particles like bullets or marbles, namely objects we can follow the trajectory of. Instead, examples of classical waves are the Mexican wave in a stadium, a wave in the ocean, as we said before, light or sound. Let's focus on the Mexican wave. Each spectator in the stadium will get up and sit down, but always remaining in their place without moving. So a wave transports some kind of information thanks to the collective oscillation of smaller elements. However, differently from a particle, we cannot draw a trajectory. And in this sense, if you want, you said something very good before, because if you think about the superposition of the position, we have a wave. But let's get further. So another difference between waves and particles is that waves can also travel through objects, and a part of the information carried by the wave can pass through a material. Think about the sound. Have you ever had an annoying neighbor who plays a music instrument and won't let you rest? Well, I was the annoying neighbor playing the piano.
Just wanted to say, usually I'm the annoying neighbor
I am,
playing
yeah,
guitar.
I can totally relate, but we are annoying. We are annoying. Yeah. But here the sound, which is a wave, can be transmitted through the wall and even tickle your ears. And conversely, if you throw a tomato, it will unfortunately not be able to pass through the wall. But this is because the tomato is another example of classical particle in a sense. But in quantum physics, this is no longer true. And the distinction between particles and waves is no longer there. So quantum systems have an intermediate behavior. We would need a third name to be really clear on this point. So let's use the term quantum particles. And this is called particle wave duality, which in a sense means that quantum particles propagate as waves and hit like classical particles.
Okay, so these are waves and particles. So this is the difference between them. So meaning like a quantum object, like a photon would be a quantum object, or an electron or a neutron, right? They can be both, or they feature properties that are like intrinsic to a particle or to a wave, but they somehow superimpose until you measure it. Once you measure it, so think back to the Schrödinger's cat, you open the box and you want to check, is it a particle or is it a wave? if you measure one of these quantum objects like electrons or photons?
Well, there are experiments on both the sides. There are experiments that shown the wave nature of particles. For example, the double slit Young experiment that showed that electrons are able to experience diffraction, which is normally something that we know from light. But on the other hand, there are other experiments that prove the particle nature of light. For example, with the photoelectric effect of Einstein. So the behavior of a quantum system sits really in the middle, and you can have more particle behavior or more wave behavior depending on the situation. But the object you listed before, photons, electrons, neutrons, protons, and whatsoever, any particle you can think of, has to obey the particle wave duality. So its behavior sits in the middle between the wave and particle behavior, which are classical ideas. Quantum sits in the middle, as we said in the
Okay.
beginning of the episode. Yeah.
Okay, cool. So maybe let's come back to this contrast thing. So quantum mechanics is like a theory of the small world, of the atomic length scale, even on shorter length scales. And then you have something called general relativity or classical physics, which is describing the everyday world we're living in, a meter, a kilometer, on larger length scales, and they are still not compatible with each other. So with this larger length scale classical physics, you cannot explain things that happen on an atomic length scale, and vice versa, right? So purely quantum mechanical theory cannot explain like our everyday life. Is that correct in a sense?
Partially. So we have classical physics, which sits in the middle and is able to explain things that happens on scales of length scales that are everyday life scales. Okay, you can even in a good approximation explain the motion of solar systems. Not fully, but in a good approximation you can. Then problems happen when you are at the atomic scale, and there you need quantum physics, or on the planetary length scale. Here you need another theory, which is not classical physics, which is called general relativity. So we have these three players, okay? We can connect general relativity with classical physics. We can connect quantum mechanics with classical physics, but we cannot connect quantum mechanics with general relativity. So the problem is in merging the theory that explains atomic scale with the theory that explains planetary scales. And if we get a theory able to make quantum mechanics and general relativity consistent, we would have the theory of everything. But still, we don't have it, and we have lots of problems that we still cannot understand, like what happens inside of a black hole. We would need quantum mechanics for investigating inside of the black hole, but with the theoretical instruments that we have so far, we are not able to do that.
So a black hole is kind of an object where quantum mechanics and general relativity comes together, or both play a certain role within such an object.
We know that both plays a role, but so far we can have a good understanding of a black hole just with the theory of general relativity. We can explain almost the whole behavior of a black hole, but there are some phenomena like the black hole evaporation, or understanding what happens behind the event horizon of the black hole that general relativity on its own cannot explain so good, and should be complemented and should be able to account for problems that happen on small scales again, but in a purely general relativity problem, let's say. So there are a couple of contradictions, and we are currently seeking for the well-known and desired theory of everything. I mean, string theory and loop quantum gravity made progresses, but still they are incomplete.
Okay, so these two theories you just mentioned are approaches to bring both length scales, quantum mechanics and general relativity, together and to combine it into a universal theory of everything.
Yeah, precisely.
Okay, so that would be, yeah, I mean, it's already in the name, theory of everything, but that would indeed explain probably everything because all length scales are covered.
Yeah.
Okay. Cool. Then maybe come to a more practical part. Besides understanding black holes, which is probably not the everyday use case for a normal human nerd or whatever. Why is quantum mechanics important, or what can you do with it? What application is directly linked to quantum mechanics or based on quantum mechanics theories?
Yeah. Beside the, answering some question about natural phenomena, you can also do lots of stuff with quantum mechanics. Some modern technologies are based on quantum mechanics, like laser or LED. These are technologies that everyone uses a laser in life is based on quantum mechanics, or also solar cells, important for the environment, are based on quantum mechanics. There are some medical techniques which are based on quantum mechanics, like the magnetic resonance imaging (MRI), or some experimental tools based on the atomic and molecular spectroscopy, which are based on quantum mechanics. Or, your cell phone is based on semiconductors, on transistors, and whatsoever. And these are all objects that have been engineered through quantum mechanics. Superconductivity is a phenomenon that can be explained through quantum mechanics. And if you think about the super fast Japanese train, they are so fast because they are based on the magnetic levitation, which is again a property of superconductivity, and superconductivity is a truly quantum theory, quantum phenomenon. And in the end, also quantum computers, which lately appeared, there are super fast machines able to solve certain problems like very complicated database search or simulation for modern medicine. So these are quite a few examples on technologies based on quantum mechanics.
So all these applications more or less exploit then these quantum mechanical properties like superposition, entanglement, or other effects that are intrinsic to quantum objects.
Yeah, exactly. Yeah.
Okay. Great. So these were all the questions on my list, which I created a few days back, and with the help of a lot of people, which hopefully listen also to this episode. Maybe we make second episode and continue the theory of quantum mechanics, and maybe by then there is a theory of everything. Let's see. How is the field evolving? Is there a quantum leap to be expected in the near future? It's hard to predict. It's impossible to predict. But what's your opinion on that?
Well, for the theory of everything, I have finger crossed, but also very, very ready to wait for some years. But purely on quantum mechanics, basically, every kind of material you can think of, there are super smart people working on that, making research, and all of these technologies that we have listed before are ongoing projects, ongoing works, and they are perfecting them in a beautiful way. So definitely it's something that will bring us an innovative step
Mhm.
forward. Yeah.
Cool. Great. Is there anything you still want to add to this episode?
Well, just let me underline that quantum mechanics is super cool, but also super counterintuitive. I mean, we in this few minutes we've talked about some very weird concept like superposition, entanglement, and particle wave duality. So don't get discouraged if you don't grasp the whole meaning in the first approach to quantum mechanics. There are people that still are struggling in the field with correctly understanding, and there are people that says that if you think you've understood quantum mechanics, you haven't at all. So that's normal, but it's also super fascinating. Love it.
Yeah, yeah, it was a very fascinating episode and very, very nice and very detailed answers. And I think in a very, very cool, yeah, explanatory language. It was very nice to talk to you. Yeah,
Thank you very much, and thanks for having me.
cool. So take care and bye. See you.
Bye. Bye.
Well, that's it for today. If you have further questions about quantum mechanics to Gian or to me, feel free to reach out and drop me a short message. The best thing about this podcast is that it's about you and that everyone can participate. So if you want to share an exciting story about your science, your academic life, some crazy experiments, or any other nerdy stuff, feel free to contact me. And let's see, maybe I welcome you on some future show. Thanks for tuning in, take care, and see you soon on the next episode of Your Friendly Physicist and Other Nerds. Bye.